Good afternoon, everybody. Welcome to the September UQRUG. Good to see a number of people here making it despite it being the mid-semester break. Thank you for coming in person as well. This week, or this month, I should say, Raúl is going to be giving us an overview of parallel computing using R. So it's basically ways to more efficiently use the cores in your computer to make your code run a bit faster. He'll go over how to do it, how it works, and some examples of it making code a bit faster. So hopefully that is something that's useful to you. I think you'll find it interesting. I've had a look over the slides already, and it looks pretty cool. I'm keen to start using it in my code. As always, before we get started, for those new to RUG, RUG is a gathering for users of all different skills. We're all here to help each other solve problems, ask questions, give answers, share interesting resources and tips, and also just hang out. So if you don't really want to pay attention, but just want to do some coding in the background, you're more than welcome to do so. You can get to our website by going to uqrug.netlify.app. So that's this link here. I'll put that in the chat. Why not? I keep looking at the laptop that's in front of me and it confuses my brain. All right, I'll pop that in the chat. There we go. Hello, David. So that's our website there. If you go through to the website, you can find a bunch of resources that we have on there. We've got past and upcoming events. I mean, it's all past events because this is the upcoming event here. What else do we have? We've got our past meetings. So you can see a full sort of meeting minutes, basically, of all the meetings that we've done, all 41 of them. This is number 42. Some links to some community groups that do similar things. And then this little document looking thing here will take you to the Hedge doc, which I don't need to click on because I've already got it open over here. And I will also put a link to that into the chat too. How about that? I can find the chat again. There we go. So, of course, we meet the last Wednesday of every month from 12 till 2. So that's right now. And we'll get started today by going through the ways of working. So if everyone can go to the link that I just put in the chat, so go through to the Hedge doc here. What I'll get you to do is click the little blue pencil edit button up here so that you can add your name to the list of people who are here today and also start adding your questions. Once you've added your questions to the page, Raúl here will go through the intro to parallel and foreach. And then at the end of that, we'll have some questions, of course, but we'll finish up with answering the questions that you've asked. Everyone's added their names. People who have questions have added them. So I guess I'll pass it over to Raúl, who's going to give an overview of using the parallels and the foreach package.
So first of all, I'm going to hand you a little R code just for you to be able to follow my example. Okay, it's very simple and it should work in any operating system. Operating systems here in parallelization is quite important because not every system works with every form of parallelization in R. So, okay, you have to stop sharing.
Quickly stop sharing there.
I'm going to share my screen and go into the presentation.
I just muted it. So
So without further ado, I'm gonna go to my presentation. Is basically ways to parallelize things in R using two packets, Parallel, which is very popular. I'm sure you already heard of it, and foreach. So why to parallelize? I don't know if you have worked a lot with heavy and intensive data processing in R, but at some point you will have realized that it never reached 100% CPU. if you run it normally. So it's always like 25%, 30%, but never goes above that. And why is that? Well, basically because R just, I think that's, because R just run on one single thread by default. I mean, there is no way to change that on normal R. So to change that, you actually have to do some tweaking to just upload some packets, special packet to do that. So there are functions that, oops.
Sorry, I'm trying to fix it.
Worries.
Keep going.
There are functions that are easily parallelized because they are independent. For example, in this function right here, if we run this function, it's basically a loop for every number between 1 and 10, just do a square of every number between 1 and 10. So you can do it like normal, and this loop will go to the first number, to the square, give you a result, go to the second, give you the result, and so on. But if you have multiple processors, you can just upload every number, one in each processor, and just do the square at the same time, and you will gain time. Obviously, this is a stupid example because it doesn't take any time to do that, but well, anyway, you will gain time. The important thing is that you need independent operations. You cannot parallel in interdependent operations because obviously if you need the previous one, you cannot parallelize that. So that's basically any waveform of parallel, not only in R, but any parallelized thing in Linux, for example, works the same. So it is possible to run a parallelized process in R, but you have to use some package design specifically for that, because R by itself is not designed to run parallel process. So parallel is the most used package. It's included in the R core system, in the base package of R. So you don't have to install it. You can simply load it by library parallel. Well, some basic concept, because we need this before starting to load some examples and all that. So basic concepts. When I talk about a core here in R, it's intended as an individual processing unit within a CPU. I know there is different definitions of cores, but for R, it's basically an individual process unit within a CPU, being virtual or physical. So when I talk about clusters, R need to recruit these cores before actually use them. So to do that, it basically gives an order to the operating system and form different recruits several cores to form a cluster. And within those cores, R will do basically open a new R session within each core and run the parallelizations there. So it's not exactly that R runs a parallelized operation. It just basically open an independent R session in each of these cores and run the parallelized operation there. So it's a little bit different of regular parallelization. So some basic coding for this. You can actually know how many cores have your computer with this order here, the dead cores. It's a very basic order. You have to first charge the parallel library. So library parallel and the dead cores. It will be giving you a number. In my computer is 8, for example. Then you will have to make a cluster. So the order is make cluster, pretty intuitive. And the number of cores that you want, it doesn't have to be the maximum number of your cores. It can be any number within your core capabilities. Then you will have to register this cluster before using it. if you don't register it, it will not work. And do your operation there. And when your operation is done, you have to actively stop this cluster, because if not, or it will keep running on the background. You won't see it, but it will keep running and give some errors down the way. So you always have to stop the cluster after using it. To see the status of a cluster, there is another order to do that. Is basically show connections like this. You don't have to put anything in between the brackets, and it will show you basically the status of the cluster, of any individual cores, what are they doing, and so on. So basically, R have two methods of parallelization, and this is when operating system becomes very important. Basically, you can parallelize using sockets or via forking. It's very different. So sockets, basically, there are a lot of technical things here, but just to highlight the practical thing, basically a socket just launch a new version of R in its code. So as it is a new version, you have to import all the packets you have to load, because it's a clean version of R. You have to import all the variables in your code. They will not be imported by default. So you have to be able to import them to the new sessions, load again all the packages, and so on. And the forking approach basically copies the entire version of R that you have now running. So you don't have to upload any packets. Everything that you have loaded until now will be copied on the version of R that is running on the background. You won't see it, but it is. So basically, forking is easy to implement because you don't have to do anything on the background, but it has its downside, obviously. So basically, socket pros and cons. So the pros are basically that socket works in every operating system. So it will work on Windows, it will work on Linux, it will work on Mac. It doesn't matter. And each process is 100% independent to each. The cons are that each process, because of how the cluster is made, each process is unique and it will be slightly slower than the forking process. And the variables and packets, as I have said before, must be imported to the created cores. So that's inconvenient and make it also very complicated to implement. But also I have to say, if you have to work in Windows, this is the only way to do it. So you have to do sockets. So forking, the pros is that it's slightly faster, not a lot faster, but it's slightly faster. It's not necessary to import all the variables and packets, which make it relatively easy to implement. But it doesn't work on Windows, so don't even try it. It doesn't work. And when you run it in graphical systems, like for example RStudio, it's slightly incompatible, so it will be causing weird behaviors, failures, errors everywhere. So it doesn't work with RStudio. So if you use it, RStudio in your work, then you will have to do it with socket. Is what it is. Well, in this session, for these examples, I will be doing sockets, not forking, but you can check macapply. It's basically the same function for forking. So if you go to the presentation that I think it's online, you can just click on this and it will redirect you to the actual RStudio page. No RStudio, it's R instructions to do it. So not really that difficult, and it's not really that different. So first, just to go to the actual packets, Parallel is basically the most used one, is constructed to function as an analogous process as apply, for example. So every apply function will have its equivalent in parallel. So that if you know how to use apply, you will know how to use parallel because it's basically the same. So it's basically apply a function to a vector or a data frame or whatever. So basically, here in this table, you have the equivalents of the apply function. So for the apply, the normal apply, the input is a data frame or a matrix, and it will output a vector or a list or an array. You will use in parallel parapply. So it's basically it sends the function, and instead of putting apply, you just put parapply. It's quite simple. The sapply has its own equivalent in par_sapply, and lapply will be the equivalent will be par_lapply. So basically, the difference between those three is the same as in the apply function. So you have different type of inputs and different type of outputs depending on which one will you use. In this presentation, we will use sapply because the output I want is a vector, not a list. I could use lapply, but it will require one more function to make it work. So just to simplify, I will use sapply. There is a special versions of parapply. If you need to apply a function to rows and columns, you have parapply or par_c_apply. It's more or less the same as parapply, but it will be doing a bit less of post-processing, so it's a little bit faster. So basically, that's the only advantage. If you need help with apply, there are a lot of manuals over there to explain what's the difference between the three of them. So I think I won't be covering this in this session because I don't think it's necessary right now.
They're just loops.
Yeah, it's
Apply to functions.
So for each is a different package. Is designed specifically for looping. So the apply function is also looping, but it's more specialized for functions. This is not really used only for functions. So it's basically, as its name entails, is for certain vector, for example, or for each of these numbers, do something. That's the basic construction. So I have a couple of examples here. So for each these two numbers, do something. So as you can see, the way of constructing the function is way more readable than apply. So it's easier to implement because it's pretty direct to what we read. So for each by default, we'll give you list as an output, but it has a way to combine the outputs in different ways. So for example, in the second function, it's the same function, but I apply this thing, the combine thing, which basically combines the result into a vector. So it's interesting. But you have to be very careful in how do you build this because it has some limitations. For example, in this function here, I'm basically trying to do a sum, is A plus B. But here I'm saying, well, for every number from 1 to 1,000, and for 10 repeated 2 times, so 10 and 10, do A plus B. So basically here, as you can see, the output is only 2 numbers. If you have different dimensioning for each, it will be taking only the first 2 dimensions of the biggest one, or the first type of the first dimension until you arrive to the dimension of the B parameter, and only do that. So it's kind of limited that way, and you have to be very careful on how you build these kind of functions. So by itself, for each do not parallelize, but it can be combined with parallel and another function called do parallel to allow parallelization. So basically, we do what I said before. So we load all these packages, 3 packages. For each, the library for each, you have to install it before, because it's not on the basic package tool included with R. You make the cluster. In this case, I make 2 cores in the cluster. You register the cluster and then do your function. In this case, well, it's the second example I gave before, and then you stop the cluster. There is a difference in time here. We will see it later with the example. And the output is the same as before, as you can see. I give you here in the presentation different forms of the combine thing here. So for example, C is due to concatenate into a vector. You can C bind or R bind to make matrices and do operators with it. So basically you can do sums, you can multiply, anything you want if you are processing numeric data. So it's quite flexible on what you can do. So I am going now to the example. So if you can, at the same time as you are doing this, you can go to your RStudio and open the code I gave you. So you can run it more or less at the same time as I do my presentation. So in this case, I'm gonna go here and do it with you. It's basically this code. So if you need to install this package, if you don't have this package, so you basically can run this, install package. Oh, was me?
I don't know why I did that. It's still working.
Okay.
That's strange.
So basically, you go to install packages and see for each and do parallel. You can just run this. That's all. And the first thing I do is just to create a function. What the function does is not really important. So basically, this is a function to try to determine if a number is a prime or not. It basically is a loop inside the function that does a division and trying to try to see if that division is an exact division or not. And basically do all divisions between 2 and the number to see if we have an exact division. And if you don't have it, it will return a true or false, depending if it's a prime or not. So it's basically that. You don't have to go actually in this function. It's not important. The important thing is that it takes a little bit of time just for us to see the time difference when using parallelization or not.
Yeah.
You just have to understand that.
So this part's not important for understanding parallel. This is just something that takes a bit of time to run.
Yeah, exactly. Yeah. So we need something like that, because if not, we will see like a small difference of time and we really don't see the difference. So that's why I will use as my data, I will use 10,000 random numbers. So that's also not important. It's completely random between 1 and 100,000. So that's my database. So basically, if you go to the code, you only have to run from here to here, and that's basically. Sorry, I have some things here already. So that's basically what I have done, is creating a function that it will be here, and a list of number that will be completely random. Okay. So the first thing we are going to test is the regular for order. So I think almost everyone knows now how to use a for order. It's quite simple. You actually learn this at the beginning of learning R. So basically it works more or less the same as for each. Is for any number in this length, do something. So in this case, from every number in the list of numbers, I'll do the prime thing. So the result I need is a data frame with a list of numbers, and if it's prime or not prime. So the result will be a data frame in this case. I want to highlight this before continuing. What I did here is create an empty vector, or not empty, in this case, all truths, but it will be filled with zeros, for example, basically to allocate memory before actually running this function. This is very important when you are doing any kind of process, but it's especially important when you do parallelization, because you actually want to, or you are constructing big vectors or big data frames. Because if you do it inside the loop, you are actually making the computer to recalculate the memory you need for this vector. So it's very important to pre-allocate the memory before that, because you will reduce a lot the time needed for this process. It's actually very important. So first I create the vector, the result, and then I will do the loop within this vector. So basically, to run all this function, it'll take approximately 5 seconds, not so much. So this is the second part of the code here, from here to here. So basically, you just run all this, and it will give you an output after 5 seconds or so with the time difference. Time difference, in this case, 6 seconds, slightly different, but doesn't matter.
A question.
Yep.
This one is socket method.
This is sockets, yes.
Okay, and how many cores? You're only doing it in one, or you're already?
No, in this case, I am not parallelizing anything.
Not yet. Okay.
Not yet.
Yeah.
Not yet. Yes.
Okay.
This is not parallelization. This is just a for command, simple for command in one core in this case,
Got it.
because it's a default setting for that. So going back to the presentation. So on the next case, this is not parallelization either. So this is for each without parallelization. So basically, the structure is quite similar to the for thing. It's the same example, but constructed a little bit different. So for each I in the length of the vector, just do the function is prime. So it's the same thing. You will have to notice here that I'm not pre-allocated memory. So this is exactly the same function as before with a different approach, but it's more or less the same, but without the pre-allocation of memory. Just for you to see why the pre-allocation is very important. The result will be the same. It's a data frame with true or false with all the numbers, and the time difference, as you can see, is quite different. In this case, it's 6 point something seconds. If you go to the actual code I give you, run it, and it will give you the second time frame.
So this one's taking longer, not because it's the for each package, but because you didn't pre-allocate.
Exactly. Okay. It's taking longer just because we didn't pre-allocated memory. This function, the for each, by itself, it doesn't pre-allocate memory. Apply, for example, it does, as it knows what will be the output, it does pre-allocate memory. So that's the difference between for and apply. It's quite a really important difference.
I want to point out something that you didn't touch on, which I think is really neat. Just back on the code.
Yeah.
The way that you set up the time difference, in case people missed it, you can see on line 53, it says start time, which just records the current system time. And then at the end, it gives you on line 58, the end time, which records the current system time, and then takes one away from the other and then prints that. And so it's a really simple way of doing a benchmark of how long does it take to actually run the thing, because it'll get the system time, run the code that takes 5 to 6 seconds or 20 seconds, and then get you the time. It's just such an elegant way of measuring how long it takes. It's cool.
Yeah, there are another function that does that with the actual code, but it will be giving you 3 times, so I didn't want to go there.
Yeah, there's benchmarks and micro benchmark and all sorts of stuff, but this is just really simple code for it. I like it.
So now we are starting to parallelize. So this very same package for its parallelize. So the code is a little bit different, but more or less the same. You have to actually upload the packages first, the parallel for each and do parallel. First, you have to detect your cores. In my case, I will be doing with all the cores in my computer. So I will detect cores and assign this as a variable called cores. In my computer will be 8. I will run make cluster. So I will make a cluster of 8 cores and register this cluster within my R session, and just run the code. So basically it's the same, but instead of saying do, I say do par. So it's the same construction, but the different thing is here. Instead of do, is do par. If we go back, you can see here I did a do process. In this case, do par, but the construction is the same. So do par is basically do this, parallelizes. So the result again is a data frame, but the time difference is way lower because I have used 8 cores instead of 1 core. So that's a pretty huge difference. To run that, just run the next part of the code. Here.
And this is, again, you don't do the pre-registering.
No, you don't.
So it's
do
still
the
faster, even though you're not doing that.
Yes, it's faster, but it's still not completely optimized in this case. So that's the small things that you have to take in account when you do this. So apply is, well, it's not as readable as for each, so it's not as direct. But in this case, I will be using sapply that will output a vector. So sapply in my list numbers is prime. So it's very short, but it's not as direct as the other one because you actually cannot read what this bit doing here. So with very complex things, apply can be quite messy sometimes. So it depends on what you want to do. So basically, sorry. So basically, the result is the same, a data frame, and it will be output in 5.4 or something. And so it's more or less the same as 4, if you recall. But the 4 that had pre-allocation of memory. So here as apply, just note that the output will be a vector with the same size as list numbers. It actually by itself pre-allocates some memory to output a vector of the same size of list numbers. So in this case, we are doing pre-allocation of memory even if we are not directly doing it, but the function will be doing that for us. So that's why sapply is much more efficient than foreach in this case. If you don't do it, if you don't pre-allocate memory by itself. So basically, this is the smallest part of the code right here. Run it, same as the other ones. It has a chunks of code to measure the system time, but the important part of the code is just the line 93, and that's all. Yeah.
Question from the previous chunk of code.
Yeah.
Do you have to install all of these libraries in each of the nodes?
Uh,
Or as in, like, yeah, you have 3 libraries, right, that you install at the start. Then you identify the nodes. And then do you have to install the libraries again, or
no,
is
no, you have to do only one
copy?
time. Yeah.
Okay.
But well, the interesting thing with Quarto is that you actually have to run its part of code as independent thing. So I just wanted to put everything in each slide
Yeah.
just to make it simple to know what you are inputting and all that. But this, you just have to run it one time. And
Okay.
also,
Oh, so the things that you're running within each node, are they part of base R?
yes,
Okay.
in this case, yes.
Okay, okay.
Yes. It's a very simple function in this case. So yes, it's part of base R. So for the last part, we are going to use parallel. The function derived from parallel, in this case, parseApply. So this will be given is equivalent to sapply. It will be inputting sorry, it will output in a vector in this case. Okay. So basically I do the same. The course, this actually you don't have to run this every time. It will be just into your computer if you have run it before. So this in this case course will not be changing. You can make the cluster also one time. If you have to run it several things, you just have to run this option just one time.
Per
because
session.
yeah, per session, because actually you are constructing the cluster, but you are not registering the cluster. But for every single thing that you have to do, you will have to, oh, actually I didn't register the cluster here, sorry. This is an error on my part. I think I just misaligned.
That's the one above.
Oh, sorry.
Yeah.
Oh, there's an error here. Here. I was missing this one. Sorry, I just committed an error. Actually, it worked. So it's not amazing. So basically, what you have to do every single time is register your cluster every time. Do the parapply function. So you have to actually put this in your code because it's not in the code I give you. And just run the whole thing. And at the end, you have to stop the cluster. That is very important because if you don't do that, the cluster will be running on the background. That will be having huge repercussion if you are, for example, in an HPC. If you are still running the thing on the background, you will still occupy cores in the HPC. So it has a lot of things that you have to consider there. So we'll just run this whole thing. Another difference in this case, as it is parallelized and it's also we also pre-allocated memory within the function of parapply. The time difference is much lower than the other things. So in this final part of code, I simply wanted to check my results. So basically, what we are doing here is just to check if all data frames are identical or not, and they are.
So the output's the same.
The output is the same, just for you to check that all these functions are equivalent one to each other. This is basically to make a data frame of the of the times that we have calculated. And this is a bar plot to actually see it. It's basically a way to see it with more efficiency. I have the output here, so we can study it. So for the first function that we ran, it was optimized with memory pre-allocation. So you actually take a little bit less, 1 second less than for each. That was not optimized for that. For each, if we parallelize it, even if we don't do memory pre-allocation, it will be much faster than for and for each. S-apply is more or less the same as for, because it actually has memory pre-allocation already embedded within the function. If we parallelize S-apply, use par S-apply, you will have the best time difference between the different examples I made before. So that's basically it. So if you want to run it, so if you want to run it on your computer, it's more or less the same. I added a little function to print the data frame we did before, just for you to say the actual numbers. But well, that's more or less it. You can do almost everything within that you can do with functions, loops, and all that. It's not very recommendable that you made a very complicated loop. You can do it, but you have to be very, very careful on what you will be outputting and all that, because actually parallelizing can be tricky because you don't see what is running on the background. You actually just see that it's running, that's all. So it's quite difficult to know what you're putting and all that. So you have to be very careful on that. And well, it is perfectly, you can run it in HPC clusters. I didn't run it in Banya yet, but I have run it in the computer cluster in my institution, and it works perfectly. So I did sucking, not forking in this case, because I need to check my results in Windows. But I imagine that forking will be perfectly fine with HPC computer. I don't know. I really don't know because I haven't.
Yeah, while we were doing that,
that's all on my part. So thank you very much.
David is trying to say something.
Oh yes.
I'll
sorry.
just try talking again, David.
Sorry, you got me?
Yep.
Yeah. Yeah. So I'm very curious to know what Parallel thinks is, or the do Parallel package thinks is the number of cores available to it in a running job. And the bad news, well, the dangerous news is that it thinks that it's got access to the full HPC node. So I ran a little test just now. I just asked it to print out the value of cores. And for a job where it was supposed to run within 4 cores, it thought it had 192. That is going to cause a big problem.
That's a big problem because what my function does in this case is just detect the maximum number of cores available in the computer, and in this case in the cluster.
Yes.
So basically,
but what I had hoped would happen is that because the job is running within a tightly controlled batch computing environment, that it should have detected the 4 cores, not the physical 192. So that's something we might have to work on. There's an environment variable you'd be able to use for it, and then that would be
actually there is in Parallel, when you use Parallel, for example, here. So this make cluster function, I just put cores here because I just wanted to use the maximum number of cores, but you can actually put 4 in this case.
That's true, but you would ideally you want code that can run on 4 or whatever. Let the job defines the environment, and then the cores. It'd be good to auto detect the number of cores, but it has to be the correct value. So I think
Oh yes, so it
there'll be
can
a way to do that. I'll just do a little bit of digging while we're just chatting.
probably you can do that somehow, but I really don't know how.
So it's detecting virtual, like the virtually allocated cores rather than the physically available cores. Is that kind of the
it's all of the above. So there are 96 cores, and then there is a virtual core associated with each core. So it's grabbing all 192. It would bring the machine to its knees if it or probably kill your job or do something. It would be ugly. So let me just find you a bit of code that would help.
Well, I have a question.
Yep.
If you were talking before about how forking is faster than socketing, and that you use the MC, does it become MC?
Oh yes.
Apply instead of power apply? Is that basically the way that function works?
It's not exactly like that. I mean, it's
because can you just do a quick swap, and instead of having power apply, you use MCL apply sort of thing, or
no, it's different. If we go here, yes,
it's
a little bit different. Yes.
Like you test it on your Windows computer, and then when you need to move it across to a Linux machine or to the HPC,
you actually cannot run it on your Windows computer. So that's why. It's not because of RStudio. It's just not compatible.
Yeah, of course.
So basically, you have the whole explanation here. It's a little bit different, but
it's the same source from Michigan University, right?
Oh yes. I think here you have Mac apply. So it's basically one function in this case. It's not 3 different functions. I think there is one with L apply, but there isn't one with S apply. So it's a little bit different. Okay, so it's not Mac S apply in this case. It will be Mac L apply, and you have to do something to actually output the whole thing. So it's a little bit different.
But that structure still looks quite similar to
it's similar. It's exactly the same because it's based on apply, but
see, you could almost do a quick swap.
Yes.
Like there's not too much changing the code.
No, it's not too much sense.
You could use the same layout that you
create. you have a lot of personalization here. So you actually, if you want to run a very, very efficient run, you will have to go to the Mac apply function instructions and actually do a lot of things. But the basic construction is this, yes. We have a lot of questions in the chat.
Yeah. What I might do.
Oh yes, there is not a way to actually know the memory here that you will be using. There is no way to actually calculate that before. So that's one thing.
That's just that.
Okay, that's just the link to this page. So basically, all the links are in the presentation that I think Nick already uploaded it. So you can check there all the functions.
Well, I might take over screen share. Yeah, so you can get the slides from today by going to the UQRUG website. If it will let me go to the UQRUG website, there we go. If you go to the events page for today, it's linked there. Actually, I think I put a link to it on the Hedge doc as well. Yeah, just there. So if you go to that link, which is, yeah, just there. I don't know why the internet's being so slow. Oh, it's a broken link. What did I do? All right, I'll fix that link. I checked that earlier. Yep. Okay. So if you go to the events page, and then go to today's event, which is this one. All the slides are right here.
Where do you get the recordings?
What's that?
Where do you find the recordings?
I'm currently, so the question is, where can we find the recordings from the sessions? I have them. in Zoom. But I haven't posted anywhere yet. So I might do that from this month onwards. I've created a YouTube channel and I'm going to start uploading them. So I'll do that for this month and then start working my way backwards for previous months, and I'll send that out in an email.
So basically everything that you see in blue is a link that you can go click on that.
Oh, sweet.
Yeah, so for those who attended RUG a few months back, this is all created using Quarto. So this is Raúl went back to the other month and looked over those things and made these slides using Quarto. So yeah, I think it's really cool that you did that.
Raúl,
Yeah.
How do you bring the results from each cluster together if you needed to do so? Like, do the clusters get assigned a number or something when you do the identify?
Yes. So the question is, just in case you
Yeah,
didn't have it. So the question is, how does the R session retrieve all the results from the cluster? Basically, all the function parallel for each, all that, just take it as the final form. So you have to actually consider that the final form will be usually a list in the case of foreach. In the case of parapply, it will depend on if you do sapply or lapply, but it will be always a function. So you have to, if you need to output something, you have to do it with return the function or something like that. But yes, it will be always a list, vector, a simple numeric thing. So actually outputting, for example, a data frame can be quite tricky. You have to actually, because it's just designed to give you very simple results. So it's not that easy. If you need a very complex data frame, you will probably need to use foreach with a combined thing to give you a data frame in the end. Yes.
Thank you.
No worries.
All right. If anyone does have any other questions, feel free to unmute or pop them in the chat. I'm sure David is going to return soon with the results of his playing.
Yep. Where am I?
He is. And while we wait for that, we'll have a look at some of the questions that we've got happening. Oh, we've got a question about fur, which is the per equivalent of parallels.
Yeah.
But it's using futures, which is another parallels package.
I never use it, but I know it more or less. Yes. So it's basically the same, but using parallel function for
yeah, if you're familiar with per is another way of creating loops, or running functions through a loop, basically, in a similar way that the apply family does, but it ties in more with the tidyverse, and then fur is connecting per functions with the future map function to give you fur. So that's why it's part of the futureverse instead of the tidyverse. But yeah. Anyway, we'll go back to the actual question.
So R in this case, well, I don't know if there is a way to limit your memory. Actually, R is not designed to run with a memory limit of HPCs. R is made for personal computers. So when a personal computer reaches its limit, so basically it goes way slower. In the HPC, it will try to allocate more memory, but the HPC will say no, and the whole process will crash. So I don't know if there is a way in R to limit your memory. Maybe there is, because there are a lot of functions to do HPC computing. So there is probably a function, I don't know what, sorry. I use a lot of processes that require a lot of CPUs because they require a lot of parallelization, but they actually take very low memory processing. So in my case, it's just CPU computing, not memory computing. Sorry, I cannot help you with that, but I'm sure there is a function to actually limit that.
So Ryan has said, I don't think you have control over the memory of each child process. You might want to use data table from previous presentation. It uses OpenMP for parallelization. Could be more efficient.
Also, memory pre-allocation could help you, because if you do not do memory pre-allocation, actually it's taking a lot more memory than the process will be using with actual pre-allocation of memory. So maybe that will be improving your thing.
So yeah, potentially trying that same process using data.table instead of using just a standard data table. Sorry, a standard data frame or a tibble. Using data.table to create data tables might be a better way, is what Ryan suggested. I have no idea. I haven't.
What footer maps does? It's basically binds the table together, or?
So that would just run read table on everything listed in the paths here as a loop. So future map you read as path by.
Okay.
Might be one for if David has any ideas there in terms of that. I don't know if
just trying to find
you have HPC perspective on that.
well, the memory is allocated to the job, and if you've got multiple cores in there, then that memory is utilized. It will, if you exceed the amount of memory you've asked for a sustained period of time, like 30 seconds or something, it will probably kill the job as a sort of preservation mechanism. But yes, if you've got if those big tables were of differing sizes, I guess if the totality of what the parallel processing would require fits within the memory you've requested, that you shouldn't have any problem. Linux will sort itself out.
So it's sort of like asking if there's a way within R to limit the amount of memory that it's allowed to use. Is that?
No, I don't believe you need to do that. It will. Yeah, I don't know that I would take that approach. I mean, you basically ask for the memory that you've got available to you. I mean, you've got two terabytes on most nodes and 4 terabytes on some nodes. So memory is not usually an object, not usually a problem. But
so if Julio is having jobs failing because the memory's being exceeded, how would you prevent that then?
Ask for more memory. Up to the, but not joking. I mean, it's still well, if you're using more than 2 terabytes of memory, then you've got a pretty big problem to solve.
There's a different issue, right? Yeah.
And then maybe what you do is you send it. Instead of doing the parallelism within a single job, you do the parallelism across multiple jobs, and you do a job array, and you take big table 1 and do that in one job, big table 2 in another job, big table 3 in a third job.
Right. So splitting up the work basically amongst more.
Yeah, because it's often where I find people come along with this beautiful little R code that they've had running on their laptop, and then they want to go big, and the fact that everything happens within one piece of code is incompatible with what they're trying to do on HPC platform, where you've got lots of machines and lots of resources on each machine. So if you could recast that code so that it took as an input the value of the name of the file, then you could run each of those on separate. So in fact, you wouldn't be using a parallelism mechanism inside R at all. It would be if it's trivially parallel, then you could divide and conquer it by running it over multiple jobs using job arrays or other tools that we have for that sort of straightforward sort of parallelization. There's a Perl based code that it's called Parallels, and it will fire off multiple processes in parallel and manage making sure that they all finish and come in return. And people have been using that sort of instead of job array. So it's there's various options. But yeah, if the total memory request is too great, if you're doing something in parallel, then you just got to stop doing as much of it in parallel.
Right.
And Julia, do you know if the processes are completed or they just keep running when you run out of memory?
Well, the system will. Well, it depends. If the batch system recognizes that your job has exceeded the amount of memory you've requested, it basically just kills the job. Same thing if you're. We've seen this a bit with MATLAB code. MATLAB gets a bit greedy, and so people run parallel par4 loops on the exact same number of cores, and it can with overheads the amount of CPU can exceed what you've asked for, and that's another reason why a job will be killed fairly unceremoniously too. It just gets clobbered. So you tend to lose a lot of any progress you made can be lost if you haven't been writing stuff out. I just wanted to just share this. So this little experiment I conducted before. I'll just pop that in the chat so you can see that I asked for 4 CPUs for the job, but running the detect cores went down to hardware level, which I was a bit surprised by. I was kind of hoping that it would recognize the environment that it was in. So what you'll have to do basically is when you do your when you build your cluster, you'll have to use the value of one of those environment variables, which it's a straightforward thing to do in R is to set. So when you so this is just the outputs from a little test. I just took it just goes down as far as the cores, detect cores, and then prints out the value of the cores it found. So it was getting 192 for the number of cores, which is not that is going to cause problems if you do that. So you need to use a value. I think it's the CPUs per task. Well, it's if you've got one task per node, then it would be the number of CPUs per task. But that seems to also be the same as CPUs on a node if the job is running on a single node.
For reference, when I do things on the cluster in our center, I basically or use a fixed number or use a fraction of the actual number of cores that it has. Because if you cannot actually do the maximum, because it happens things like that happens all the time.
Yeah, sure.
It's not. You have to remember that R is not actually designed to be run on parallel, so it's these things.
Yeah, it's taking networks and distributing them across multiple cores, and it lends itself to certain sorts of things. MATLAB suffers from the same situation. It's very good at doing parallel for loops as long as those for loops are all independent of each other. It has no concept of like message passing interface and high the sort of sophisticated multi-node sort of parallelism that climate models and computational fluid dynamics and those sort of codes use. But it doesn't stop you doing some good work. It's just sort of where it's at in the sort of on the on the spectrum of single CPU computing through to tens of thousands of cores, the sort of exascale stuff that keeps people gainfully employed at national sort of facilities overseas. Yes, that's so I would just if you're going to try this out on HPC, just set the value of the cores for your cluster to be the same as the number that you've requested in the job that wraps around this thing. So it's just unfortunate. It's a two-stage process. Yeah.
You see, you manually put in the number of cores that you're using rather than
then use that
automating it. Yeah.
Yeah, but what I was hoping would happen was that R would ask the question, and the answer it would be what the batch system had allocated you, rather than what the physical hardware had. So that was the surprise to me, because I thought it would constrain it. So what you can do instead is, in your code, use the value of the CPUs on the node environment variable. And that way you would get, you would always have the value of the number of cores that your job required. So if you decided you were going to do four cores today, and then you run another job in a couple of days and you're going to use 8 or 16, you don't want to have to change your R code every time. You should be able to.
Oh, there is another order that actually may be useful. It's not from Parallel. Can you check this thing on? It's not Parallel, it's Parallelly. That's more or less the same. It's available workers. Apparently it works with a Slurm code, so maybe it will work.
Okay. So the Parallel package.
It's another package, so it's completely different, but it may work with this to detect the cores. It's from the library. It's from Parallel. Supposed to report the number of machines that the Slurm has allocated in your job. So maybe it will work.
People.
Well, while David does that, I'm going to see if I don't think there's any other questions that cropped up. If anyone does have any questions, feel free to put them in or ask away. But what I was also going to say is that we already have a plan for the next highlight of the month. So this month is obviously parallelization. Next month, we're going to be having a look at doing machine learning. So Raimundo, who was here earlier, but is not here any longer, I think he had to leave early, will be giving an overview on doing machine learning in R. So if anyone's keen to come along to that, please do so next month. I still send out the survey asking people what they want to do, but because I had someone put their hand up for something that a number of people have requested, machine learning, so I've lined up Raimundo to run that next month in October. So that's something to already look forward to. But we're still going to stick around and see what David comes out in terms of resolving the detect cause issue. But does anyone else have any questions? I'm also wondering, does anyone realize that they could make their code more efficient using parallels? I feel like yours potentially could have.
Mine is just the most inefficient of everything that It's about threw my phone or computer out the window 7 times.
That's interesting. Okay. So what it gives you, actually lists, it names the machines that, but it gets the number right. So the length of that vector would be would be correct.
So
Well,
just
yeah.
throw a length around it then, right?
Yeah.
Oh, so you actually have to do length of that, and you will have it.
Yeah.
Okay,
So that would work.
it will work.
Yeah. But I think the main thing is that you request a single node. In terms of a HPC job, you have to ask for the job to run on a single node and for there to be one task, and for the CPUs per task to be whatever number you want, 4 or 8 or 16 or 96 or whatever. And just bear in mind that well, if it's a some sort of parallel, completely independent parallel implementation, and it doesn't start falling over itself, then you could go to quite a large number of parallel fork processes. I think it would just be yeah.
Right. So this is the other way of doing it.
So you grab the value of that environment variable, and that will always be what the batch system knows, and that ultimately is what you need to know, because it's yeah. So presumably, I didn't have to build any of those packages; they were already available on the build of R on Bunya. So
that's the advantage of that one.
Yep.
Whereas this one, you're going to have to load in parallelly.
Yeah, but it's already built, so it's not. I didn't have to build it or anything. It was just available as a package to use.
Yeah, they both work, but this one's probably the easier one to use. Cool.
Sure, and that's CPU per task, as long as the number of the end task per node is 1. So that would be that's a pretty standard thing anyway. I might make a note to just put something else into the user guide about that.
That's good. Glad you're able to make it. I can see that a question is gradually appearing here, so we'll let Grant finish typing that out, but we will have a question about for loops at some point in time. Cool. All right, looks like a bunch of code has been dropped in. So Grant has the same code for 6 participants, made 6 lots of code, worried that's efficient. So here's the code. Tidyverse, load in some R data. So are you wanting to create a for loop that does that for all 6 participants rather than running it 6 times and then parallelize that? Is that kind of the question? So is it basically that you'd have 6 of these being loaded in, they're all effectively the same, and you're wanting to do that entire process to all 6 of them? Because that can definitely go in a loop. Anyone feel like doing some coding on the fly? Yeah. Thank you. I guess you could make a list of each of the sub for like you could do.
You can even look for patterns if
Yeah.
they have more or less the same construction. Is look for the pattern, parse data, blah blah blah. Build a vector with the names and then do all the rest in a loop. Which should be fairly easy, huh? Basically,
Yeah, that's what I was thinking.
so this will be something like that. The pattern will be path will be 0 theta. Something like that. Pattern will be first. So here this will be defined as the list files or something like that. Or list files. So now I have a problem with the English and the Spanish keyword. I don't know how to code in a Spanish keyword anymore. What we don't want to do is at the frame.
So I'm just typing out, I'm copying Raúl's code very, very quickly. So the first step here that he's going with is to create a list of all the files that you're wanting to load in. So using list files will look in a particular path for you. So it's looking inside our folder here, which is where the data is presumably contained. And then with list files, you can then give it a pattern to then follow. So the pattern is the first part of the file name. And so what this will do is it will create a list of all of the different files that follow that pattern inside that folder and assign that to the list files vector. So once we've got that list, we then need to basically loop that list around all of this. And that's what Raúl is doing. He's written a for list at the moment.
I'm just taking your,
Which is a and just creating a basic loop to go around that. And now he's just currently writing each of the different steps, like a form of each of the different steps that you have here. And then once you've gotten that loop written, you could then put that loop inside of a parallel and presumably make it run a lot faster. If it needs parallelizing, it may not, depending, it depends on how big those are and how I mean, If that is an absolutely huge file, then parallels might be useful, but given the things you're running on it, it probably doesn't necessarily need to be parallel, but yeah, depends.
Let me just check it. Code. It's
Oh, David left.
see.
So here's that. All right, I think we might, like, once we've got this one going, that might be everything for today. Felicity, I see you're still hanging around. Did you have any questions at all? You're just seeing to hang around to see where this one goes as well. Yeah. Yeah, fair enough. Oh, David had to leave. Cool. You want to just you drop that into the thing?
Yeah, I think it will work.
I've got my script out, but that's just a little part. I'll let you keep coding. I'll talk about what you've done. Hey, so for that. Yeah, just get all that. Yeah.
No, it's like that. Yes.
So what Raul's done here is created a list of files, created the for loop here. So for file in list files, so that will be each individual file in that list. It will turn that into a data frame and assign that to the first, to A. It'll then
whatever it is.
Return the length of the first column or that condition column, and then return the median of the time column.
It's basically what you were doing, but
so that's creating the data frame, giving you the length of that one, giving you the median of that one, and then it's the same process for the rest of the things, just doing that same sort of stuff. Skipping it's instead of running it and then returning it, it's returning it as part of a function that creates that particular thing.
the return, what would be this in this case, a list or a vector or a output?
A vector.
Multiple returns will work in this case.
Interested to see what it does.
Yeah, I know it's messy, but
so that code should work, Grant. I'd be interested to see if you ran that, if it would give you, that should just give you the length and the median for each of the different files in the list. And if that works, then you can do the same process for the rest of the different things you're wanting to do there. And should make it a bit more efficient.
I'm not sure about the return part, but it will be quite easy to fix if you put it in a vector or something like that.
Cool. Go. Cool. Yeah, give that a go. Let us know how you go. And you can always come back to this and let and edit this still and tell us how it happens. But if you do run into any further issues or you have more questions about this, you can send my team an email, training@library.uq.edu, and we'll happily happily go further with this with you. Either over email, or we could do like a little consult or something. Cool. Well, I think that's everything for today then. Thank you everybody for coming to UQRUG during mid-semester break. And thank you again for running that. I am absolutely going to be using Parallels more. And I wasn't previously, so I really appreciate it.
I hope so. It's a very useful tool.
Yeah, definitely. All right, well, everyone online, we'll see you next month for the October RUG. So that'll be on the 25th? I should know, I put the dates in. Yeah, on the 25th at 12 p.m. for looking at machine learning, which I'm also keen to learn more about that. So, all right. Thanks again. See ya.